G'day, welcome to the one and only lesson in our final unit looking at analytical techniques. In this final lesson, we're going to look at infrared spectroscopy. For our lesson objective, we're going to investigate infrared spectroscopy as an analytical technique and understand how to interpret IR spectra. So when it comes to organic chemistry, organic synthesis is one part of the challenge. You've got to work out how to synthesize a molecule. Say if you're doing new research, you're working out a pathway to synthesize a molecule that hasn't been synthesized before. You've got to work that out. But it's one thing to just say that you've got the compound, you've then got to confirm it. You need to have evidence and data, and you've got to be able to, like I say, confirm that you've actually synthesized the molecule that you've said you've been synthesizing. This is where this whole field of chemistry called analytical techniques comes in, and it is a really fascinating area. There's a whole plethora of different analytical techniques and analytical instrumentation, ranging from the very simple, the very inexpensive, to the very complicated and very, very expensive. Unfortunately, we only look at one particular analytical technique at this point in time on IR spectroscopy, but later on you will visit some more of these techniques, and like I say, it's a really, really fascinating area of study. So IR spectroscopy is an analytical technique, a technique to analyze a sample, whether you're determining the structure of an unknown or just confirming a molecule that you've synthesized. It can be used to help determine the identity of a chemical substance. Its biggest use comes from its ability to identify certain functional groups that are present in a molecule. And in fact, IR does have a lot of limitations when it comes to deducing a structure, but what it does do, it does very well, as we'll see. So it uses the IR spectrophotometer. So we abbreviate infrared to IR. A spectrophotometer, an example of an instrument here, where you place your sample in, you jump on the computer, you do the analysis, and you end up with an IR spectrum. Spectroscopy is a whole area of study on itself, which is how essentially light and matter interact with each other. So how matter interacts with electromagnetic radiation. And we can utilize it in really, really fascinating ways to work out structures of molecules. So IR spec, as you might be able to guess from the name, it involves the interaction of matter with the electromagnetic waves in the infrared region of the electromagnetic spectrum. So the electromagnetic spectrum, as we dabble into a tiny little bit of physics here, is all the possible wavelengths and frequencies that we can have of light. Now, our visible light spectrum is this small little slither of it. That's all that we see as human beings. But as we increase or decrease the frequency, there's all these other areas of the spectrum that have interesting and unique properties. And just based on some of the names, you might be able to see that we can use these for lots of reasons. For example, radio waves, microwave. I'm sure you've heard of a microwave. You've probably got one in your kitchen. X-rays in medical imaging. So there's lots of useful things that we can take advantage of when it comes to how the light interacts with matter. What we're focusing on in infrared spectroscopy is how matter is interacting with the electromagnetic waves corresponding to the infrared region, so just above our visible region there. Now, there are other spectroscopic techniques, for example, ultraviolet visible spectroscopy. This operates in the UV visible spectrum part there. That's another kind of analytical technique, not one that we're particularly interested in right now, but you can see that it's also on the spectrum here. So we're interested with how matter interacts with light in this section here. So what is going on in infrared spectroscopy? The spectrophotometer detects the intensity of infrared wavelength as it passes through a sample being analyzed. Very simply, a molecule is going to absorb certain areas, for lack of a better word, of frequency in the infrared spectrum section, and it won't in other parts. So it's all depending on what bonds we have in the molecule and the properties that those bonds have. So then what you can get is you can get the information about what has been absorbed and what has not been absorbed. And because this is characteristic of certain bonds and certain functional groups more specifically, then we can make inference about our unknown structure. Organic molecules absorb radiation in the IR range, and the frequencies they absorb are characteristic of their structure. So it all depends on the bonds and what kind of atoms we have and the mass of those atoms, and some other pretty advanced stuff that we're just going to gloss over. So it's based on this idea of resonance frequencies. Molecules will absorb only specific frequencies depending on their structure. There is a natural frequency that the bond vibrates at called the resonance frequency. So you can imagine all the chemical bonds in a molecule vibrating. However, based on the nature of that bond, due to the atoms in that bond and a bunch of other factors, there's only a specific frequency that they're vibrating at. This is the natural frequency that they will vibrate as, and it's called the resonance frequency. So what we do with the IR is we blast it with the whole IR spectrum, and what it will do, the parts of the spectrum that corresponds to this resonance frequency, this sort of natural frequency that the bond is already vibrating at, it will stimulate a larger vibration and the energy will be absorbed. So depending on what the resonance frequency of the bond is, then it's going to depend on what part of the IR region it's going to absorb, and consequently how much of that light is getting through to the detector in our IR spectrophotometer. There are a number of forms of vibration: stretching, bending, and twisting. We'll have a look at this quickly. It's not something we need to be particularly concerned with at this point, but it's fascinating nevertheless. So, the bonds in a molecule can, like it says, vibrate in certain ways. So let's just have a look at these. So we can stretch the bond. So this is exactly what it sounds like. The bond is stretching. Now it can either do this symmetrically or it can do this asymmetrically. So if we imagine a symmetric stretching, these bonds in whatever our molecule is are stretching in and out symmetrically, so in the same direction together, which I will act these out for us. But if you imagine a symmetric stretching, and I'm that central atom with my two fists can be my two bonds, the stretching would essentially be, how can I get in the frame here, like that. That would be the symmetric stretching that they would be vibrating like. Now compare this to asymmetric stretching. So asymmetry meaning that it's not symmetrical. So they're still stretching, but they're not doing the same thing as each other. Rather, this time, the bonds would be going like that. They're still stretching in and out, only they're doing it asymmetrically. So that's the first kind of vibration. Then we can have bending. So this is where the vibration occurs where the bonds are bending. So we can have symmetric bending, where they're bending down like that, and we call this scissoring, because this is a kind of scissoring motion. So again, I will demonstrate it. So this would be, if these are my bonds, this would be scissoring like that. So symmetric bending, and then you could have asymmetric bending, which would look like this, which is where we have rocking, which if I, again, act it out, you got your bonds there, and you would have rocking like that. That would be how they're vibrating. And finally, you have twisting, which is where we imagine them going into and out of the plane. So twisting, these both have pluses, so you imagine them coming towards you together and then going back away from you together, which again, I got my bonds here, it would be like that. So they're going in and they're going out together. And then the final kind, so that's called wagging, and then the final kind is the twisting, which is where they're doing it asymmetrically, which if I work out how to do this, I guess that would be like that. They're sort of vibrating that way. So there is my demonstration for you. They're the different ways that the molecules can vibrate. All right, so why am I telling you all this and acting like a fool here with my actions? Well, each unique type of this vibration, remember they're unique based on the atoms that are bonded. This will give us a characteristic wavelength in the IR region because they're only they're only absorbing a very small amount of the section of the IR region, and therefore our detector won't see that section, if that makes sense. So we can present this on an IR spectrum that plots the percentage absorbance, so how much is being absorbed, or conversely percentage transmittance, but they're pretty much the same thing, just sort of opposite, but they look exactly the same. So the percentage absorbance of light on the y-axis against the wave number corresponding to the IR region on the x-axis. We can then identify if a functional group is present based on the absorbance pattern by fingerprinting the position, shape, and strength of the peak against a database. So this term fingerprinting implies that it's unique, right? So let's look here. We've got the wave number down the bottom there, and we can see that there's areas where the certain bond is unique of that region of the IR spectrum. So we can see, for example, our halogenated carbon with a halogen, they can be anywhere around here depending on what they are, what the halogen is. Our ethers around there, our carbonyls around here, our alkenes, our C double bond ends. There's a bunch of carbon nitrogen, carbon sulfur, carbon triple bond carbon there, and then the alkanes, amides, hydroxides, amines, etc., etc. So depending on where we get the peak, but not only where we get the peak, how big the peak is, how what the shape of that peak is, and the position of that peak, and that will tell us what kind of functional group we would have present in the molecule. Now you don't have to memorize these numbers by any means. You will get these given to you. So for example, here is the data booklet, an example of which you would get in an exam. So if you scroll down here, scroll down, and you find the section on the characteristic infrared absorption frequencies for some selected bonds. So what you can see is we've got the bond type, the functional group that contains that bond. So for example, there can be, we've looked at carbonyls recently. Carbonyls can be in esters, carboxylic acids, ketones, aldehydes, amides. They're going to appear at a specific absorption range that is, again, unique to that particular bond type based on the resonance frequency of that bond. So we can see where the peak is appearing, as in whereabouts on the x-axis, and then we can also get information about the character of the bond, if it's about the character of the peak, sorry. If it's a strong peak, if it's a weak peak, if it's broad, if it's sharp. So this all gives us information that we can use to conclude what functional group is present. Now before we look at a spectra, let's just discuss some of the limitations here. IR does have a number of limitations, as the nature of the rest of the molecule will shift the energy that certain bonds absorb. Can't be too specific when quoting the bond's absorption frequency. So that's why we have these ranges. And some of these ranges, can be quite large, 1040 to 1300. And also because of this, we can have a high overlap of the absorption bands. So you can see here that our halogens can overlap with our ethers. We got a bunch of different ones that are overlapping in this region, a bunch overlapping in that region. So these are all limiting how much information we can get about the structure. Where it becomes most useful is in combination with other analytical techniques. And when you're doing characterization of organic molecules, you'll often use a number of different techniques together. For example, an NMR with an MS, or an IR with an NMR, so on and so forth. So it's a good supporting evidence to go with our results from other analytical techniques. Okay, so you will end up with something like this. This is the IR spectra of ethanol. So you can see we got the wave number down the bottom here, percent transmittance or percent absorbance. It'll be the same looking spectra, it's just which way your numbers are going, so don't worry too much about that. What I want you to do is, if you pause and if you find a database for IR peaks, like I just found before, you can just Google it. See if you can identify the characteristic bonds that are present in this molecule. I mean, it's easy because you're given the molecule. Match the bonds with some of the peaks. Give that a go, pause, and then we'll check the answer now. So what we see here is we see this broad peak at around this region. Now this shape and this intensity of the peak, this is very, very, very characteristic of an alcohol bond. So if you ever see something like this at this position with this broad shape, you're thinking alcohol, right? So let's compare that to our data book here. We've got no H of a alcohol. So we're going to have a strong, sharp, between the region of 3200 to 3600, or 3580 to 3650 if we're considering the hydrogen bonding. Well, let's just keep it simple. And that's exactly what we see here. Where's this one? 3358. So we're lying right in that range there. So that's telling us we got a hydroxide hydrogen-oxygen bond. We also have CH bonds, sort of alkane bonds. So if we look here, we have a CH of an alkane. We're going a strong peak, 2850 to 2950, so that's quite a specific range. 2974, we're lying right there. Finally, we're going to have the carbon-oxygen bond, which would be corresponding to these peaks, or that peak down there. So the CO of an alcohol, strong, 1040 to 1300. That's what we have, 1050, 1090, exactly in that range there. So it's a really good tool to confirm that we have certain functional groups present, but like I say, with its limitations, it's best used in conjunction with other analytical techniques in order to analyze our molecule and identify its structure. And with that, we have finished our lesson on infrared spectroscopy. We have analyzed an infrared spectrum of a simple molecule to identify functional groups, and we looked at the data booklet for the functional groups required. There are your tasks. Pause and work through, consolidate your understanding on IR spectroscopy. And with that, we've not only finished our final units on analytical techniques, we've also concluded the organic chemistry section of our course. Very well done. Congratulations. I will see you around. Have a great day. All the best.